What I want to talk about is, I'm playing the words here, ecosystem of cyber infrastructure that we've been involved with for a number of years now. I asked Mike last night if that was okay. I didn't want to get, crucified for misusing the term here in this audience, but he seems to think it's okay, so I'm okay with it. What we've been working on for 6-7 years now is the Predictive Ecosystem Analyzer. It's basically this framework which kind of connects a number of community-built ecological models, and it deals with a lot of the data problems that are associated with that. Mike gave me this little image here where things we've done with him, ingesting data, processing, analyzing, connecting has been a big part that I've been involved with, and so forth. These are all problems that are pretty common with regards to, I would say, this kind of work. And so with regards to this, NSF has been working to address this, not just for biology, but for all scientific domains that seem to have similar needs with regards to the data they're working with. So I want to serve kind of like an advertisement here for some of the activities that have been happening on the Cyberinfrastructure side for NSF. So back in 2009, a number of task forces were put together to kind of address the problems and challenges around science and the needs for Cyberinfrastructure. Things with HPC and big data, and education and software and so forth. Hundreds of pages of reports came out of this thing and was eventually distilled down to this document, which you've probably heard of at some point, called CIP 21, kind of describing cyber infrastructure for the 21st century. And it basically comes down to 3 points. One is, rather than building out these large, monolithic, do-it-all pieces of software or infrastructure that are difficult to sustain, don't do that. Build many small components that interoperate, kind of connect together. And basically can be plugged into each other to build out bigger ecosystems as needed. Kind of like the internet is today, there's a lot of different components that build that out. Make them sustainable by doing that. Make it so that they have communities around them that support those components. Maybe there's multiple versions of those components. Survival of the fittest kind of thing, and basically the overall ecosystem can thrive. And a key aspect of this, the first one, is enforcing this strong relationship between the people building this software and the scientific community. This mantra, don't build it and soon they'll come, has been ingrained into our heads for the past 10 years in the Cyberinfrastructure side of things. So that's been pretty key, is working very closely with people like Mike Leeds to build out these components so that they're actually useful and meet the needs of the community. So this is kind of a diagram that's come out of a couple of PI workshops on the data infrastructure building blocks in the past couple of years. And what I want to highlight here is this ecosystem. So at the bottom, what you have is the raw resources, whether they be NSF provided, like through Exceed, or commercial things like AWS or university resources. And then as you go up, you get this stack of stuff that kind of helps you deal with data. And these are all kind of cryptic with weird names and word numbers and so forth. But as you kind of go up, they get more community specific for portals type things. In the middle, there's kind of this glue type stuff that brings things together to deal with data transfer, data transformation, data analysis, and things like that. And so what I'm going to do is just highlight a few of the ones that I'm involved with. So the blue ones are the ones NCSA touched on in some degree. And just kind of give an idea of what these things are. But I would encourage everybody to kind of get familiar with all of these things. It's a little difficult at the moment, but there are these efforts like the science gateways, for example, that are happening through NSF that kind of trying to shine some light on some of these aspects. Also the big data hubs, getting involved with those communities will get you in kind of in the loop with regards to these kind of efforts that are happening here. And so they touch on all different aspects, as I mentioned, data transfer, data transformation, all these different things. And their idea is to build out an ecosystem where you can put these things together to meet your needs. So the first one I'll touch on is the one I'm working with Mike called Brown Dog. So this effort, basically what it is a data transformation service. So the idea is you give us some data. I have no idea what this data is potentially. I do something, conversion. And so the Brown Dog will take care of it. So it basically provides a suite of data transformations that will convert this file or data set into some other format. So for PCAN, the Predictive Ecosystem Analyzer, we do a lot of these. And so these have to do with converting different formats for the different models that come out of the ecological community. And so each one has a different format. There's a lot of different data sets being involved with too, and they're all in different formats. So a lot of back and forth between these formats that have to take place there. And so you do conversion, see what's in there. Okay, this is the image, right? So the next step is, well, what if there's a large collection of these things and they're all unstructured data, and I need more than just raw unstructured bits and bytes. So Brown Dog also provides these transformations called extract. And so what these do is basically they take that raw data and turn it into something a little more useful. And so in this case, for an image, you get basic metadata like the resolution of the image and stuff like that. Great. But you also get other stuff, like, for example, I detected a face in this image. I detected somebody wearing glasses. I get OCR text if there's text in this image. And then you get more scientifically relevant stuff as well, depending on the extractors that are available. So for this particular case, there's an extractor for green infrastructure. So it's looking at the foliage in the image and telling you how much green foliage there is in this image. It shows you that. There's a model of how much human would prefer this landscape architecture versus another. So there's a score for that that's being spit out in this metadata here. This is a metadata in represented in JSON LD. It's a way of representing data, metadata for the internet between services. It's convenient for these services to use. It's relatively human readable. You can kind of see the OCR text and so forth in there as well. But the idea is then a machine could then use this, another program or algorithm can take this information from the service, not have to do these transformations themselves, and just take the outputs and do whatever they need to do next in terms of the actual science there. And so for cases like PCAN, the infrastructure behind this is also important because there's some large data sets like NAR weather data, for example, which is inconvenient to be transporting around. It's many terabytes of data, and then when you only need a piece of that, why do you want that entire data set? So Groundhog will actually cache that data on its infrastructure, and then you'll run these transformations on that, and only pack the piece that you want. So it's a little more convenient in that sense that you don't have to worry about actually moving around large data sets like that. So in PCAN, basically, there's a little checkbox in the bottom left here where it says use Groundhog, and basically these transformations between different models will actually occur there. Having this capability in a service like Groundhog also allows for the inverse of this as well. So we created this little demonstration app where basically these people from these other probability models can go here to get data in the formats for ED, for example, or SIPNet. They can just go here and download the data in those relevant formats with the same infrastructure. There's this transformation in the background provided by Groundhog, whether it's used by PCAN or this web app. It doesn't matter, it's available for all, so it doesn't have to be duplicated. So it's kind of like an artificial data repository for different data sets like NAR and others. So the idea is to make this something that's other applications can build off of. So in some of our other geoscience communities, ArcGIS is very popular for if you're working with data. So in this case, there's a Groundhog tool being incorporated into ArcGIS to find trees and LiDAR data. So basically, there's a piece of LiDAR data, delineate the trees. The Groundhog service kind of is called as a plugin to that, and you can see little boundaries of the trees in this image here. Because it's a separate service, it can be called by other pieces of software as well. So there's an open source alternative for ArcGIS, QGIS. So here's the same exact thing in QGIS, same plugin, basically called there. Excel is very popular in science, so basically there's a plugin we support for Excel. In this case, with regards to that green infrastructure example, it's just a latitude and longitude coordinates. You call Groundhog to find all the foliage that you observe across this path that you take on this coordinate system. And basically, it just populates that spreadsheet with a couple of columns saying, you know, the greenness that you encounter across that. And this is pulling all kinds of different things in the background from Google API and Street View and things like that to get those images needed to do that and greening that's extracted. So it's a lot of stuff in the background, but as a user, you don't care. Well, you do care, but in terms of actually executing it, maybe not. So basically, you get that information right just like that. Simplifying code, so basically this is an example of some student code to find biospells or rain gardens and satellite images, you know, reducing the length of that so that basically you don't have to duplicate the parts that do those kinds of extractions. It's just called Groundhog and significantly reduced from 200 lines of code to 40 lines of code, things like that. And then to an extreme case, just Windows file manager, and just most recently, right-click on a file, convert it, right-click on a folder, search it on stuff that's not even indexed in it, based on extracting metadata. And most recently, this past couple months, we've been working with Box. It's like Dropbox with another company to incorporate Groundhog into Box. So basically, you can search for metadata that's extracted from, in this case, galaxy images to find similar-looking galaxies in the surrounding. Those examples we put there. So that's one example. So it's a data transformation service. So the idea is that the communities that would need that capability of wrangling data don't have to reinvent those things and can actually use this and share pieces of data that create themselves with these other communities who can then leverage them as well. So second one I'll just mention quickly is called Clowder. This is a new effort that just got kicked off. Actually, funded and kicked off. It's been living for quite some time as an input state. And so what it is basically kind of a smart Dropbox. So it looks like Dropbox on the surface, but it's really much, much more than that. It helps with the aspect of sharing data, publishing data, curating data so that it's reusable by others. Just putting the files out there by themselves is enough. I'm sure if I and so we've used it for a number of different communities, building it really from a grassroots effort from the ground up to kind of establish it, and now driving it with a NSF CSSI award to kind of really bring it home. And so the main thing there is this idea of active curation. And the idea is basically around using analysis tools, kind of like the roundup was doing data transformation for brilliant, and specifically machine learning to kind of help curate data as it's ingested into this Dropbox-like thing. So basically, as data is put into this Dropbox, these machine learning tools, these other analysis tools and so forth, will automatically fire off based on the types of data that are being uploaded and do things like extract, the meaning text, extract back into trees and species of life data, rivers and things like that, and annotate this, tag metadata as the locations of where these things are at, just by uploading it into the system. And so this is a complicated landscape in terms of data sharing utilities. Clowder is not trying to duplicate any of those, but it kind of fits in this middle area here in terms of that staging between the raw sharing of data to the publication of usable scientific data and helping with that, getting across that spectrum there. And so kind of tools that are included in this are, again, leveraging some of the stuff that was done on the ground as well as things like finding pieces of a cell and biopsy image and tagging that, finding flood basins or old rivers and old documents and overlaying them together so that you can see them and see how rivers meander. This is for our critical zones efforts that we're involved in. Handwritten recognition, type stuff of documents and so forth and so forth. Tracking people and seeing who they talk to and things like that. So more relevant to this community, I want to highlight some of these. So it's, again, an example with LiDAR data. Finding the trees and species of trees based on green LiDAR data. Building these massive mosaics of images based on satellite data or drone data. This is something we've been doing quite a bit, actually. Finding flood basins. In genomics, we've been doing this stuff where we're looking at plants and crops and counting the number of leaves. How tall is the plant? How green are the leaves? And things like that for genomics aspects. So this Clowder framework is basically built to be as extensible and customizable as possible to meet many scientific community needs. That's the idea with regards to sustainability, broad needs, reduce reinventing the wheel kind of aspect of things. So making it so that it's usable by many different efforts. And so one other aspect of this accessibility is with regards to metadata. So it's completely customizable with regards to the metadata that it supports as well. You can basically plug in a different schema and it'll support that. In this case, it's for example ODM2. And it'll have tools to kind of help users in upload data and meet those requirements in metadata as well. It's offering tools that are available to the system as well. Let's keep this slide for a minute. Analysis, that's kind of what we do with PCAN, is pretty important these days. There's this idea that you don't want to download large data sets. It's inconvenient. It takes too long. Sometimes pretty difficult given network constraints. So whenever you can, if you can run analysis right next to the data, that's pretty important. So this is kind of a theme for the past number of years. Move the compute, not the data to this. And so Clowder supports that not only through these extractors that fire off the data at the data center, but also through this new capability, which is actually worked with the National Data Service in their workbench tool that we plugged into Clowder, in a way, another building block. Basically what it is an app store of random tools. And so they're all contained in these things called Docker containers. And so they're completely encapsulated. And so and along with the dependency, so all a user sees is this little GUI, this tool, and it says launch, and they should launch these tools. And Jupyter is very popular these days as an analysis of way of analyzing data, RStudio and others. But anything really could be here. And so what we've done for like our phenomics project, TerraRef, which has a petabyte of data, and you don't want to download that, is provide this workbench next to Clowder. So basically, to run a Jupyter notebook, you can just go here and launch it, and it directly mounts the data, that petabyte of data, right in that notebook, as well as these other tools they have in this case as well. So basically, you don't have to download that massive data set. You just run these tools right next to the data set, given that there's a computational resource next to the data set, of course. And so we've used Clowder for a number of efforts. I just saw the critical zones mentioned. We're working closely with IML CZO and more probably with all CZOs to support their needs. Lots of heterogeneous data there, lots of unstructured data that needs to be wrangled and brought together and shared. TerraRef is an RPD project, again, massive amounts of data there, doing things like different sensor types of data, massive stitching of crop fields every day, terabytes every night, so dealing with that kind of thing. And industry partnerships, can't talk a lot about it, but I'm working closely with Syngenta, who are leveraging a lot of these things built for the scientific community and contributing back. They actually are hardening the heck out of this particular framework because they're using it in production. And this all comes back to the scientific community. So these kind of relationships with industry are important for those kind of things. So, they leverage us, we leverage them, and so everybody wins kind of. So overall, between these two efforts, we've done 129 million data transformations and accounting still. But ideally, with communities leveraging each other's activities and not reproducing them and sharing these things. Really briefly, one of the newer efforts we're involved in is on the bottom side of this thing. So storage, where to put the data has always been a kind of crucial aspect of everything. And so an effort is underway to kind of explore the possibility of providing a national storage infrastructure. And so this pilot effort called Open Storage Network is doing that. The idea here, in terms of the infrastructure side of things, is to leverage, again, past infrastructure investments. In this case, leveraging years of investments in networking through CC stars, leveraging investments in community building through the big data hubs, leveraging HPC investments in Exceed and so forth, and kind of filling in the gap, storage. And so at the intersection of all these things, just putting these data centers, these lightweight, I shouldn't say data centers, data appliances, containing about a petabyte or more of storage, and providing the software to kind of connect them together. So from a user perspective, it looks like one massive storage resource, even though it's a bunch of separate ones. And the idea is over time to kind of, this pilot works out, to kind of do this across the nation, across universities, near data centers, near compute resources at the intersection of networking investments and so forth. So there's hundreds of petabytes of storage that are allocatable to the scientific community based on need. And so if there's a need in terms of sharing a large data set or a particular data set with the community, and there's no other way of doing that, this is there for that. And so basically providing these appliances, ideally as low cost as possible, and so that basically they can be deployed this way, is what the effort is trying to do. So I'm going to stop there in terms of the actual infrastructure. Again, I would encourage everybody to look at the scientific gateways, at the big data hub activities to kind of see the rest of these things. We are trying to do better in terms of highlighting what's happening here in terms of the actual capabilities being provided, and these cryptic names, and having to look at the inside the word search and abstracts to figure out what's going on. To make it kind of easier to understand what's being provided, because if users aren't using it, then what's the whole point? So please take a look at those things, scientific gateways. So one thing I did want to highlight at the end of this is basically this other effort, and working with Mike, I think he appreciates this as well, is there has been this growing need, not just in terms of these components, but in terms of these people who build software. These software developers who bring best practices, who are savvy with regards to lots of different frameworks and communities, and able to work with scientists very closely to build out what's needed for the scientific community. And so there's this movement that's actually happening right now called the Research Software Engineering Movement. It's driven out of the UK largely, but it's starting to come over here as well in the US. And to kind of solidify that that's important within science these days. So right now, if you're a software developer in science, here's an example of maybe you're an RC, and in fact, I wouldn't be surprised if many of you would fall into this category here. Do you develop software? Are you the computer person in your lab? Are you left off of publications because you just do software? Kind of thing. Do you lack metrics in terms of career advancement? Are you a postdoc, but you do software? These kind of things. And the aspect is that software is important for science today. Data is important for science today. They can't be separated out. It's a different world. And so the idea is that the software development person is critical, but beyond professors and students, there's this other thing. So trying to establish that is a big deal. And so there's a lot of activity being driven out of the UK to bring this together. They go under many different names within nationally and internationally, postdocs, research programmers, computer guy. So they're trying to consolidate that as the same research software engineer. And so, this is largely what we've been doing with Michael the past 10 years at NCSA. So we've been trying to, not knowing about this movement, in fact, just trying to consolidate all these different activities and make them one, and basically establish a career path for these people so they stick around and they become trainers of new people who do this stuff and so forth. And so me and Dan Katz, who used to be at NSF, working in software there, wrote a paper about this, and it's largely really about the management aspects of this, juggling all these different projects, supporting a project that needs only a quarter of a person or half a person or 10 people, and being able to do that kind of thing and retain those people and the experience behind it. Institutional knowledge is so important with software, so when you lose that, that's bad thing. So basically preserving that aspect of things. Establishing a career path from assistant level to principal level and so forth, and the requirements behind that so that it's clear. Also for collaborators, what they get when they work with us. And so what that has done for us is, you know, as I showed up front, these bullet blocks we've been involved in, it's a portfolio of software that's sustainable within at least our little growth, and ideally bigger than that, the communities we're involved in. And we've done some big things with that. You know, a couple of, you know, crown jewels, I would say, is this Ergo effort, for example. Started with Mavis back in, it ended in 2008, $20 million effort. And it took a hiatus for almost a decade. We were able to preserve it, because the institutional knowledge was preserved in this body of RSC. For this new NIST effort, in for another $20 million that was like grateful. Well, we can start, you know, not from ground zero, we can take this, you know, large investment and keep on running with it and have to great success. And so Clowder was another example of that. It started with its O&R effort many years ago as Medici, and basically never was really funded as itself, kind of seeded across dozens of different projects here spanning many different communities, and kind of stitched together, you know, there's these common needs across all of them. Let's not reinvent the thing for each separate domain, let's have them work together and leverage each other's energy. And so we did that and successfully put together the CSSI kind of program. So I'll conclude there. This is kind of just one take of Cyberinfrastructure that we provide, you know, from NCSA. And again, I would encourage everybody to take a look at the science gateways to see what else is